The night the sky fell quiet, the world noticed in the way only scientists and dreamers notice such things, with a slow gathering of unease followed by urgent questions. Across continents, great observatories that usually fed the global community with live vistas of distant suns and faint galaxies stopped their streams. Screens that once showed tiny flickers from the deep reached blank frames. Cameras that had tracked a curious visitor slowed to silence. For hours, the hush hung over the scientific community like a held breath. People logged onto feeds and watched empty pixels. Engineers refreshed status pages and saw maintenance flags and calibration notices. The explanations arrived slowly and thinly. At first, routine work seemed plausible. Then the pattern hardened into something else when multiple major facilities reported interruptions at the very same time. Far from that quiet, however, a different story was unfolding. In a Chinese observatory perched above a mountain and buffered by careful automation, a small team kept their instruments pointing and their data flowing. They had been watching a small, fast-moving object that had captured the attention of astronomers worldwide. Named 3 Atlas, the body was the third known interstellar interloper to cross into our cosmic neighborhood. It passed through once and would not return. Its glowing envelope did not fit the ordinary catalog of cometary features. Instead of a halo composed primarily of water ice and the familiar jets of steam, its coma was rich in carbon dioxide and organic dust, a blend that raised curiosity and cautious excitement. Space telescopes sensitive to infrared wavelengths had picked up a chemical mixture that did not match what we typically see from comets formed in the inner regions of a young star system. As the visitor drew closer to the sun and brightened, observatories from the Hawaiian Islands to the plateaus of Chile focused their mirrors and detectors on the same patch of sky. Scientists raced to capture spectra and high-resolution frames, aware that each snapshot might be the last. Then, paradoxically, as the object reached a critical luminous phase, the world's most powerful Western instruments all dimmed. Hubble paused. The Very Large Telescope reported unexpected technical work. Gemini listed rescheduled nights. Even the telescope that orbits beyond Earth, built to see the faintest infrared glows, entered a lull that left many researchers scratching their heads. Social feeds filled with speculation and rumors. Amateur observers tried to keep up with modest gear and posted grainy but valuable images. Their contributions were sincere and loud, but the results lacked the precision the community craved. Meanwhile, minor observatories complained that automated requests for observation time went unanswered. Scientists who planned measurements around specific passes found their windows closed at the last minute. With each passing moment, a sense of loss grew stronger. The silence felt intentional to some and painfully coincidental to others. Where Western instruments had gone quiet, signals from parts of Asia were still active. A handful of Chinese tracking stations and ground-based observatories continued to log data and to relay it back to research centers. Word leaked through informal channels that Beijing had maintained surveillance of the visitor uninterrupted. Within days, images began to circulate that were linked to Chinese facilities. They showed 3i Atlas in frames time-stamped at the precise moments when the Western arrays had gone dark. At first, the photos were treated as routine releases. Then scientists noticed details that made them sit up. The frames from Chinese arrays revealed a detailed and dynamic coma. The tail extended like a gossamer thread, and jets of material rose unevenly from the surface. As analysts looked closer, they saw subtle, regular changes in brightness. Where most comets shine with chaotic flickers, this object showed pulses that repeated with a regularity that did not fit standard cometary physics. Panels of researchers noted the pattern and began to test different hypotheses. They compared thermal models with observed responses to sunlight. They looked for instrumental artifacts. They ran simulations of rotational behavior and of asymmetric outgassing. Some possibilities held briefly, then unraveled under closer scrutiny. Public release of the images came with little international coordination. The National Astronomical Observatory of China posted a sequence of high-resolution frames, along with analysis that highlighted the object's unusual chemistry and its rhythmic light variations. The timing of the publications aligned squarely with the period of silence from many Western observatories. Headlines quickly framed the event as a breakthrough led by Chinese science. Official responses from agencies overseas were cautious and sparse. They acknowledged receipt of the images and invited collaboration, but offered no simultaneous raw data of their own to compare notes. This moment marked more than the presentation of a curious cosmic visitor. It became a story about control of the narrative around discovery. As scientific attention sharpened, a dangerous question circulated. Could the object be reacting to human transmissions? Analysts looked at times when radar and directed radio tests had been aimed in the object's direction, and then compared those moments with the pulses recorded in its emitted light. The correlation was faint but consistent across several sequences. The brightness rose slightly after strong radar pulses in a way that researchers found difficult to dismiss outright. If the pattern held, it suggested a responsiveness the astronomical community had not previously seen in natural bodies. Explanations ranged from the conservative to the speculative. Some teams argued for complex natural processes only rarely seen in known comets. They suggested layered composition and novel mineralogy could create thermal feedback mechanisms that mimicked pulses. Others proposed that trapped gases in the object's structure could release at quasi-regular intervals under certain thermal cycles. A bold minority raised the possibility of an engineered origin, a probe that emitted or modulated light in response to external stimuli. To many, the word probe carried uncomfortable connotations, but the data compelled rigorous testing of every plausible model. The political dimension of the episode deepened the scientific challenge. Access to raw observational files was limited by national policies. Some Chinese agencies allowed only vetted international partners to view unprocessed exposures. Western scientists pressed for broader sharing, citing the imperative of independent verification. Those discussions became entangled with diplomatic cautiousness. Accusations of data withholding circulated online and in academic corridors. For decades, astronomy had functioned with a spirit of broad openness. Researchers accustomed to shared archives found themselves negotiating access in a world where strategic concerns and national pride could shape the flow of knowledge. Amateur networks became more important than ever. Observers in the southern hemisphere and in underserved regions contributed time-stamped images that could corroborate certain features. Their enthusiasm and rapid mobilization demonstrated the value of a widely distributed observation community. At the same time, the limitations of small telescopes were clear. Many claims made in public forums could not be verified at the resolution needed to test the most intriguing hypotheses. As the debate intensified, the object's dynamical behavior continued to surprise. Rather than breaking apart at its sun-closest approach, it remained intact. Thermal readings suggested the surface did not heat as models predicted. In some measurements, temperatures seemed regulated, cooling faster than expected when illuminated and maintaining warmth in shadowed intervals. Radar tracking revealed short bursts of acceleration that did not fit the random recoil expected from uneven jets of vapor. The velocity tweaks were small but precise enough to suggest deliberate maneuvering. High-fidelity frames occasionally revealed repeating geometries beneath the fuzzy coma. Analysts reported spiral grids and ridge-like structures that repeated in symmetrical patterns. Instrument teams examined processing pipelines to rule out artifacts. Several independent groups, both inside and outside of China, found similar features in raw exposures. The balance shifted toward the conclusion that something about the object's structure was non-trivial and perhaps engineered. Yet science demands more than a collection of unsettled indicators. It requires replicated findings and testable mechanisms. The public followed each development avidly. The story moved fluidly between sober science reports and imaginative speculation. Filmmakers and authors used the moment to explore themes about contact and curiosity. Schools used the event as an educational moment to teach about scientific method and the value of data sharing. Religious and philosophical voices offered perspectives that ranged from wonder to caution. The cultural conversation was wide, reflecting the universal nature of the questions raised by an object that might be more than a rock. Policymakers also took notice. The idea that control over critical windows of observation could shape who tells the story of a major discovery prompted calls for more resilient networks. Proposals included distributed arrays of smaller telescopes in many countries, new standards for rapid sharing when rare transients occur, and even an international charter that would commit signatories to open exchange in truly exceptional cases. Negotiations proved delicate. National security and intellectual property concerns complicated simple solutions. Yet the momentum for change was real, driven by the sense that discovery itself had strategic value. Within the scientific community, the event catalyzed methodological reforms. Journals and observatories discussed protocols for blinding and anonymizing early data submissions to reduce geopolitical framing. Peer review processes for extraordinary claims were sharpened. Multidisciplinary teams formed more readily, combining astrophysics, materials science, signal analysis, and spacecraft engineering to examine the puzzle from many angles. The collaborative spirit returned, albeit in a new form shaped by the lessons of a night when many eyes went dark and some stayed bright. Over months of analysis, some anomalies were resolved as instrument quirks and processing artifacts. Other anomalous signals withstood scrutiny and remained stubbornly unexplained. The best collaborative models suggested that a mix of exotic natural processes and unusual structural features could account for several of the observations. Yet a subset of behaviors, notably the precise micro-accelerations and the rhythmic response patterns correlated with directed transmissions, resisted natural explanations. That gray area sustained interest and debate, and it enforced a healthy humility across the field. The episode left its mark on funding priorities. Governments and philanthropic organizations that had been tentative about large-scale investments in observational infrastructure now saw a clearer rationale. Funding for wide-angle surveys, for resilient data archives, and for rapid response telescopes expanded. Citizen scientist programs received targeted support, recognizing the confirmed value of grassroots contributions. The appetite for an international framework that balanced open science with legitimate security concerns grew. In the laboratory, the human side of discovery grew more evident. Scientists who had once assumed that data would always flow freely across borders found that institutional arrangements matter as much as detectors and telescopes. Younger researchers watched how geopolitics could shape the pace and direction of inquiry. Those watching from outside formal institutions saw a route to participation through well-organized amateur networks and carefully run small observatories. Decades from now, historians may look back at the event as a turning point. It showed how leadership in scientific discovery can shift and how the norms of openness can be tested by strategic and technological realities. The immediate controversy faded into a deeper adjustment of practices and expectations. Agreements, however imperfect, emerged to ensure more robust global coverage of rare astronomical events and clearer pathways for joint analysis. 3 Atlas itself drifted back into the darker reaches of interstellar space, its mysteries intact and its legacy lasting. Whether it was a natural body with unusual composition and structure, or a manufactured object of unknown origin remained unsettled. The more likely conclusion, as some consortia reported, was that this singular visitor exhibited a combination of uncommon natural properties and dynamic responses that require continued study of similar objects should they appear again. The search for analogous visitors became a priority. The episode offered a compelling reminder that the heavens are not the preserve of any single nation. They are a shared environment that prompts a shared responsibility. The night when many telescopes fell silent and a few kept watching became a cautionary tale complemented by renewed cooperation. It taught scientists and policymakers that observation systems must be both technically resilient and socially robust. When rare and possibly paradigm-shifting phenomena appear, the global community benefits when data circulates openly and when analysis is inclusive. At its heart, the story of 3i Atlas is about curiosity, rivalry, cooperation, and the limits of understanding. It exposed weaknesses and strengths. It sparked fear and hope. It led to new technology and new agreements. It also offered a simple, stubborn lesson. The universe will not pause for politics. If we want to know what passes through our skies, we must design observation systems and social systems capable of keeping watch together, soon. In the months that followed, the 3 Atlas episode became a living case study for how modern science operates in the world as it is and not as we might wish it to be. The immediate mystery of the object remained, but new conversations shifted the emphasis from wonder alone to practical questions about preparedness, ethics, and the distribution of scientific power. Researchers and policymakers alike began to imagine what a more resilient global observatory would look like and what rules should govern rare events that touch every nation. First came the technical reforms. Engineers and observatory directors sketched plans for redundancy that would prevent a single failure mode from silencing entire regions. Instead of relying on a handful of massive installations alone, networks of smaller telescopes could be coordinated so that no single outage would deprive the world of continuous coverage. Fast data pipelines and standardized formats would let images and spectra move almost instantly between institutions with minimal manual intervention. Satellite relays were redesigned to prioritize transient streams and to provide fallback links if ground systems experienced coordinated interruptions. Software architects worked to reduce single points of failure in the scheduling systems that had left some observatories suddenly unable to respond. Where before the emphasis had been on building ever larger mirrors, the new thinking valued connectedness and diversity of vantage points. The second transformation was cultural. Many in the scientific community recognized that openness must be actively maintained. It is not an automatic result of goodwill. Collective habits were codified into formal agreements. New protocols required that in cases of anomalies with wide scientific importance, raw observational data be provisionally shared through escrowed secure repositories accessible to accredited researchers across borders. Legal frameworks were created to protect sensitive national security concerns, while still enabling the independent verification essential to science. The message was clear. Discovery without reproducibility is not discovery at all. Education also adapted. Universities and research institutions introduced interdisciplinary courses that combined astrophysics with diplomacy and data ethics. Young scientists learned not only how to operate a spectrograph, but how to craft international collaboration agreements and how to explain complex uncertainty to non-specialist audiences. Scientific journals tightened standards for extraordinary claims and required clear descriptions of data provenance and access. The message was straightforward: science must defend its methods as carefully as it defends its measurements. The public conversation, which had once been dominated by a few sensational headlines, matured. Media outlets refined their coverage to avoid premature claims and to place extraordinary findings within a framework of degrees of confidence. Documentary makers and authors took care to highlight the detective work of verification as part of the story of discovery. Popular science programs used the episode as an opportunity to teach the public about hypotheses, falsifiability, and the long grind of hypothesis testing. Rather than chasing the most dramatic angle, thoughtful outlets emphasized the patient accumulation of evidence that underlies robust conclusions. Diplomacy became part of the toolkit for science. Rather than treat curiosity and geopolitics as wholly separate spheres, diplomats and scientific envoys began to negotiate rapid response pacts. These pacts were designed to be activated in a limited set of circumstances. If an object of potentially transformative significance appeared, signatory nations agreed to share critical metadata and to allow independent cross-checks. Committees composed of scientists, ethicists, and legal scholars were preemptively assembled so their deliberations could begin within hours of an alert. The idea was not to bypass national sovereignty, but to protect a common interest in truth. 3 Atlas also inspired innovation in sensing technology. New instruments aimed to detect the faintest modulation of light with greater fidelity. Teams of physicists worked on detectors that could better distinguish between natural thermal fluctuations and engineered modulation. Materials scientists studied whether exotic crystal structures could account for the rhythmic behaviors observed. Engineers experimented with micropropulsion and attitude control simulations to understand whether a natural object could produce the precise microaccelerations recorded. In laboratories around the world, graduate students redesigned experiments to mimic the thermal and mechanical conditions the object might have experienced during its journey. The episode invited reflection on the proper tone of scientific statements in times of uncertainty. Scholars reminded their colleagues that humility is not a weakness, but a discipline. Presenting neat narratives in press conferences can be appealing yet misleading. The 3 Atlas case emphasized the need to present multiple working hypotheses and to communicate degrees of confidence rather than definitive conclusions that may later require retraction. In public briefings, researchers learned to explain which results were reproducible and which required further verification. They grew more comfortable saying, "We do not yet know." Art and literature responded as well. Writers explored the human dimensions of a moment when the heavens seemed to watch back. Painters and composers translated the rhythms observed in the object into new works. The arts provided a space for the public to sit with the mixture of fear and awe that scientific uncertainty can produce. Community events featuring scientists talking with artists broke down barriers and helped to humanize the long and sometimes messy road to understanding. Creative works reminded audiences that scientific discovery is a human endeavor with emotional texture and social consequences. Of course, some threads of the original controversy remained unresolved. Skepticism persisted in the community about some of the most provocative interpretations. Without a second object behaving exactly the same way, the strongest claims could not be fully tested. Yet that uncertainty fueled an appetite to find more. Surveys were adjusted and search algorithms refined to flag candidates that might otherwise be overlooked. Citizen scientist platforms introduced targeted campaigns for pattern recognition tasks, tapping a global community of volunteers who helped triage enormous volumes of data. Amateur networks proved their value not simply through noisy images, but through coordinated, time-stamped records that could corroborate or refute fleeting anomalies. The episode also encouraged thought experiments about contact. Philosophers and scholars of security studies bodies debated the ethics of intentional transmission toward unknown visitors. Should humanity reply if a clear response could be established? Who should decide? The debate revealed a wide spectrum of opinions. Some argued for a cautious scientific approach with broad consultation and slow deliberation. Others felt that a single nation should not have unilateral authority to generate a message that might have far-reaching consequences. The discussions that followed were not merely academic. They informed real proposals for governance that sought to balance curiosity with foresight. Finally, there were personal stories. Astronomers who had waited in vain outside darkened domes described the strange solitude they felt during those nights. Colleagues across oceans moved from competition to collaboration as they worked to build redundancy and trust. Young students were inspired to enter careers that blurred disciplinary boundaries. Communities that had once been on the periphery of global astronomy now saw new opportunities to host instruments that could offer valuable coverage. In small towns and in major research centers, the human ledger of the event included moved conversations, renewed friendships, and shared frustrations that matured into cooperation. When the last papers about 3I Atlas were filed, and when the immediate cultural waves subsided, the longer-term changes remained. The global scientific system learned to be more modular and to build channels that could carry the truth in storms. The old scripts about who leads discovery were rewritten into stories that recognized distributed networks as a form of strength. And though the object itself receded into interstellar dark, the reverberations of its visit ensured that humanity would be more attentive and better prepared for future arrivals that may be equally puzzling or perhaps even stranger. Above all, the episode offered a reminder of why science matters. Beyond claims and headlines, beyond rivalry and pride, science remains the best tool we have to approach the unknown. The 3I Atlas moment tested that tool. It exposed its vulnerabilities and prompted repairs. It taught that the work of observation is not only technical, it is social and political, and it depends on trust as much as on telescopes. The night when many eyes closed and a few stayed open changed how humanity listens to the dark. Future explorers will carry these lessons forward. Institutions committed to open science must build safeguards and legal clarity while nurturing international goodwill. Young scientists will remember fragile cooperation and how necessary it is to protect shared resources. The night when the skies spoke differently will be taught in classrooms as a turning point. It will remind us that curiosity requires responsibility and that looking outward calls us to look inward at our choices.